Hello students, welcome. So now we are heading towards the end of the unit. So our last topic is group 18 elements. So this group contains noble gases. Group 18 consists helium, neon, argon, krypton, xenon, radon and oganesson. All of these are gases and chemically unreactive, and they form very few compounds. Because of this they are termed as noble gases. Now we know that each and every element will try to form noble gas like electronic configuration, and if they achieve such electronic configuration then their compounds will be stable. So in this case already noble gas like configuration is achieved because these are the noble gases, so that's why they are very less reactive. So where these gases occur? All these gases except radon and oganesson occurs in atmosphere. Their atmospheric abundance in dry air is about 1% by volume, of which argon is major constituent. Helium and sometimes neon are found in minerals of radioactive origin, example pitchblende, monazite and clevite. The main commercial source of helium is natural gas. Xenon and radon are rarest element of the group. Radon is obtained in decay product of Ra, that means radium. So as mentioned, radium will decay in radon and helium. So first we need radium to produce radon. That's why it is very rare, because we do not have comparatively much amount of these type of radioactive elements, and that's why it is hard to obtain. Oganesson has been synthetically produced by collision of californium and calcium ions. That means it is not a naturally occurring element, but it is laboratory synthesized. So as we can see, Cf and Ca produces Og and releases 3 extra neutrons. Now this element's symbol is Og, atomic number 118, and the atomic mass 294 and electronic configuration. It is noble gas, so it has fully configured or fully filled orbitals in it. So 5f14, 6d10, 7s2 and 7p6. Only very small amount of Og has been produced. Its half-life is 0.7 milliseconds, and therefore mainly predictions about its chemistry have been made. Here, except the oganesson, important atomic and physical properties of other elements are mentioned with their electronic configuration in the following table. So, as the detail suggests, its electronic configuration contains fully filled orbitals. Atomic radiuses will increase with increasing atomic number, and last element is unknown because it is radioactive and it has very rarity. So that's why we do not have much details about it. Ionization enthalpies, as mentioned, ionization enthalpy values are quite high because these are noble elements, so usually they do not tend to lose electrons. So that's why removal of electron from this type of element is comparatively very hard. So ionization enthalpies, as we can see, decreases down to the group because as we move down to the group, atomic numbers will increase, so less attraction towards the nucleus will be there. Now electron gain enthalpies of these elements, as we can see, they are positive. Now all of the other elements shows negative electron gain enthalpy because these are the noble elements, and that's why it is hard to add electrons into them, and that's why it shows positive electron gain enthalpy. Usually electron gain reactions are exothermic, so it will be negative. Densities of the element, again as we move top to bottom, densities will increase because of increasing atomic number of protons and neutrons increases. Melting point, so as we can see, helium, it is mainly occurred in form of gas, but with very extreme conditions we can liquefy it, but solidification of helium is impossible, or we do not have such technologies available yet. So that's why we do not have melting point of helium. And helium is one of the lowest boiling point containing element. As we can see, boiling point of helium is 4.2 and it is mentioned in Kelvin, so it is very close to absolute zero temperature. So liquefaction of helium is one of the hardest thing. Now as we can see, as we move top to bottom, boiling points and melting points are increasing because of increasing atomic number. And then we have percentage of these elements in atmosphere. So all the details discussed in the tables are mentioned here as well. And now let's move towards its physical property. So all the noble gases are monoatomic, that means their molecules contains only one atom. They are colorless and odorless and tasteless, and they are sparingly soluble in water. They have very low melting and boiling points because the only type of intermolecular attractions is they have very weak dispersion forces. Helium has the lowest boiling point of any known substance, and this is the reason why we do not have its solid form. And it has unusual property of diffusing through most commonly used laboratory materials such as rubber, glass and plastic. Now chemical properties, so these elements as mentioned earlier, they are very less reactive, so usually we do not have much chemical reactivities obtained from these compounds. And reason for that is, as mentioned, first point, noble gases except helium have commonly fielded ns2 np6 electronic configurations in their valence shell, and second, they have very high ionization and more positive electron gain enthalpies. So usually to get reaction out of these elements we need very high amount of energies. The reactivity of noble gases have been investigated occasionally ever since their discovery, but all the attempts to force them to react to the compounds were unsuccessful for quite few years. In March 1962, Neil Bartlett, then the University of British Columbia, observed the reactions of noble gases. First, he prepared the red compound, which is formulated as O2 plus PtF6 minus. He then realized that the first ionization enthalpy of molecular oxygen was almost identical with the xenon, and he made efforts to prepare same type of compound with xenon, and successfully preparing another red colored compound Xe plus PtF6 minus. So that means these compounds are coordinate complex compounds, and by mixing PtF6 and xenon. After this discovery, a number of xenon compounds, mainly with most electronegative element like fluorine and oxygen, have been synthesized. So usually we need some strong elements to get reaction out of these noble gases. So the compound of kryptons are fewer, only difluoride has been studied in detail, and compound of radon have not been isolated. But it is identified, example RNF2, by radio tracer technique. So this type of technique gives reading about certain elements which has quite low life. So no true compound of argon, neon and helium are yet known. So how to prepare xenon compounds? So some methods are mentioned. So xenon forms three binary fluorides, XeF2, XeF4 and FeF6. With a different amount of fluorine we can get these type of compounds. So as we can see, with F2 at 673 Kelvin and 1 bar pressure, then 873 and 7 bar pressure, and 573 and 60 to 70 bar pressure, we can produce XeF2, XeF4 and XeF6 sequentially. And XeF6 can also be prepared by interaction of XeF4 and O2F2 at 143 Kelvin as mentioned. So now these compounds are colorless, crystalline, solid and sublimate readily at 298 Kelvin. They are very powerful fluorinating agents because they are attached with fluorines are attached with xenon, and it is very less reactive, or it is noble. So it easily releases the bond, and that's why it acts as fluorinating agent. And they are readily hydrolyzed even by trace of water. For example, XeF2 is hydrolyzed to Xe and HF and O2. Because again same thing, xenon is noble gas, so usually it do not tend to react. If you forcefully do so, then it will be unstable and it will quickly participate in reaction to convert itself into xenon atoms. The structure of these three xenon fluorides can be deducted from the VSEPR and the shown in figure 7.9. XeF2, XeF4 have linear and square planar structure respectively, and XeF6 has 7 electron pairs, and that's why it has distorted octahedral structure. and experimentally it is found in gaseous phase. Xenon fluoride react with fluoride ions acceptor to form cationic species and fluoride ion donor to form fluoroanions. Now next is xenon oxygen compounds. So hydrolysis of XeF4 and XeF6 with water gives XeO3. So as the reaction suggests, we can produce xenon atoms with xenon compounds in presence of water out of xenon fluorides. So different type of compounds or different type of contents of water and XeF4 and FCF6, we can create different type of compounds, and partially hydrolysis of XeF6 gives oxyfluorides XeOF4 and XeO2F2 as mentioned in the reaction. And structure of these compounds are mentioned. So these lobes represents lone pair of electrons and it has multiple of them. So this is a distorted octahedral structure because it contains total 1, 2, 3, 4, 5 and 6 fluorines and one lone pair. So this lone pair repels each fluorine bonds, and that's why octahedral shape will be distorted. So these are the structures of xenon compounds. XeO3 is a colorless explosive solid and it has pyramidal molecule, and XeOF4 is colorless volatile liquid and it has square pyramidal molecular structure.